Okay, in this example question, we're asked to determine the magnitude and direction of the resultant electric field strength at point P, which is the midpoint between these two particles here. Okay, so if that's a midpoint, that means 0.4 millimeters divided by 2 gives me 0.2 millimeters from the center of both those charges. To find the resultant electric field strength, I need to pretend to be a positive charge at point P. The positive charge on the left will repel this one, and the negative charge on the right will attract it. Notice how the force from the negative charge is smaller because this charge is smaller. Okay, I can use this equation here to find the electric field strength. Comes from Coulomb's law. So let's start with the charge on the left. Okay, it's got plus 2 charge. So the Q there is going to be 2 times 1.6 10 to the power of minus 19 divided by 4 pi epsilon naught. Epsilon naught you can find in your data sheets times the distance from the center of the charge to point P squared. Notice how I've turned it from millimeters into meters before squaring it. This gives us electric field strength like this. Okay, now to find the force from the charge on the right. I could put the numbers in again and do the whole calculation, but I'm just going to use proportionality. I know the electric field strength follows this equation. The charge on the right has half the charge, and the distance and everything else at the bottom is the same. So that means the electric field strength will also be half. So this attraction on the right hand side will be half the of 7.19 times 10 to the power minus 2. That gives me 3.6 times 10 to the power minus 2. Because the forces are both in the same direction, or the electric field strength are both in the same direction, you add them together to give you the resultant electric field strength. Okay, example 2 now. The diagram shows a plus 1 nanocoulomb charge and a plus 4 nanocoulomb charge, which are 0.2 nanometers apart. Point Q, the electric field strength is 0. Determine the distance x there, which is from the left-hand side, plus 1 nanocoulomb charge. Okay, so at point Q, I'm going to pretend to be a positive charge. I know that if the electric field strength there is 0, that's because the repulsion from both of these two charged particles is balancing out, it's cancelling out. So I can use this equation here. So I know the charge on the right has times 4 the charge of the one on the left. Okay, so that means if he wants to get the same electric field strength at point Q, when you get this is the same, that means the distance r has to be times 2 because when it gets squared, that becomes times 4 and cancelled out with the times 4 at the top there. So we know the distance from the plus 4 nanocoulomb has to be 2x, like so. So now we can form an equation, which means that if you add these two distances x and 2x together, you should get 0.20 nanometers. Okay, and then that gives me 3x. And then dividing both sides by 3, that means x is 0.067 nanometers. The final example now, determine the magnitude and direction of the resultant electric field strength at point S. S is 0.10 nanometers above M, which is a midpoint between the two charges here. So I'm going to pretend to be a positive charge at S. I'm going to be attracted by both of these charges toward the center of each charge. I'm going to use this equation here to find the electric field strength from each charge at point S. Now the R here at the bottom, which is being squared, is the distance from the center of each charge to point S. Okay, so I need to find that distance. I can use Pythagoras because I know this distance here is 0.20 nanometers because it's halfway, and the other distance there is 0.10 nanometers. So I can use 0.1 squared plus 0.2 squared and square root that, and that gives me 0.224 times the minus 9 nanometers. So that's this distance r here. Okay, so let's put that into the equation. So if we have 2 times 1.6 times 10 to the power minus 19, 4 pi epsilon naught times the distance we just calculated in nanometers squared. Okay, that gives me an electric field strength from both of these charged particles because they're both equal distance, they both have the same charge, so both of them have electric field strength of 5.95 times 10 to the 10 newtons per coulomb. Okay, however, this is not the end of the question because these two forces are not acting in the same direction, so we need to find the resultant electric field strength by using trigonometry. Okay, so first thing you notice is that the forces towards the left and right are equal and they'll cancel out, so we don't care about that, we can ignore those. It's the downward components that are going to add up together. So the downward component from the one on the left and the downward component from the one on the right will add up together, so it'll be actually the same, identical, so it'll be 2 times the downward force there, and that will produce a resultant electric field strength downward. So to find that component, I'm going to draw this angle here, theta, and Now I've got, this is the adjacent of that part, and this is the hypotenuse, so I can use cosine theta to find that component there. So I'm going to take that force and then multiply by cosine theta. Now, cosine theta is adjacent over hypotenuse, using trigonometry there. So adjacent is 0.10 and hypotenuse is 0.224. And so this would give us the downward component from one of those forces. We need to multiply this by 2 because there are two of those forces acting downwards there. So if you multiply by 2, we get the resultant electric field strength.